there. Hello there. Yes, it's been so exciting coming to your homes once again with making physics simpler with Sir Idea. In our last meeting, we looked at the displacement function of a body in simple harmonic motion. Yes. So today we'll have a quick recap of what we achieved in our last meeting, and then continue with the velocity function or equation of a body in simple harmonic motion. So if we are saying that the body or the particle oscillates around the mean position or the equilibrium position O, then if once the body is displaced, it does so with a certain speed or velocity. So what is going to be the velocity equation or function at any time t of displacement from the equilibrium position? That is what we are going to look at now. And so the velocity function of a body in simple harmonic motion. Alright, yes, fasten your seatbelt and then stick and stay as I take you through the journey of the velocity function of a body in simple harmonic motion. As I said, let us have a very quick revision on the displacement function of a body in simple harmonic motion. Alright, I'll crave your indulgence to adjust my screen a little bit so that we can have a full view of the board. Thank you. Alright, so we realize that the velocity function of a body in simple harmonic motion, the displacement function rather, the displacement equation, it's also a function. Body in SHM. So we considered a body in circular motion since circular motion has that relation or bearing with simple harmonic motion. This is the center of the circle O. So we considered a particle moving from a point A to a point B within a time t. This displacement along the circumference is directly proportional to the angle subtended at the center. And this body doing that circular motion in the circumference has done so with a certain constant angular speed or angular velocity omega. We therefore derive that the angular velocity is equal to the angular displacement over the time taken to make that displacement. Therefore, we got the angular displacement theta to be equal to omega t in radian. So that's how come we change this theta to omega t. Alright. So if this is omega t, then we realize that as the body embarks on circular motion, it is also doing simple harmonic motion. And so we saw that yes, as the object moves through the circumference, it can either be oscillating vertically or oscillating horizontally. Okay, and so at any time t, we realize that the object can have a displacement equal to, this is y, or if we project it to this point y, we saw that sine of the angular displacement is equal to y on the amplitude. Therefore, y is equal to a sine omega t. And this is the displacement function equation or function along the vertical axis, along the y-axis at any time t. If we want oscillation along the x-axis, then this is it, x cos of the angular displacement is equal to x on a. Therefore, x is equal to a cos omega t. And this is the displacement function along the x-axis at any time t. Any time t. So this is what we achieved for the displacement function at any time t. Okay, these are the displacement. So when you are asked to determine the displacement of the particle at any time t, either along the y axis or along the x axis, this is what you use in determining the displacement of the particle, okay, along the or around the fixed point O. Alright. Okay, so let's quickly look at the velocity function of a body in simple harmonic motion. So let me make quick adjustment of my board. So the velocity equation of the body in simple harmonic motion. So let's have a circle again. So what we are saying is that if the object or the body is seen to be oscillating either vertically or horizontally around a fixed point O, once the body oscillates, then it does so with a certain velocity. or with a certain speed. So what is this equation for the speed at any time t? Okay, so we are saying that the body moves from A to B. If the body is moving from A to B within a time interval t, then at any given time we can trace its displacement. So when it moved from here to this point, this is how much it is displaced from the center O. If it moves to this point, this is how much it is displaced, y1. If it comes here, it is displaced, okay, at the extreme. Okay, so if at any point in time the object is being displaced from the equilibrium position, okay, around the center O, then the object is not static or it's not stationary. It does so with a certain velocity or speed. So what is the equation for the speed or velocity at any time t? That is what we are looking at. Okay, so in a linear motion, we realize that velocity is the rate of change of displacement with time. Okay, so once velocity depends on the changing displacement with time, here too, for us to get the displacement function, we must look at how the displacement function changes with time. So our v would be equal to delta y on t, or delta t, or which is also equal to delta x on t. And that is when we are looking at the changing displacement along the vertical axis or along the horizontal axis. So either this or that will give us the velocity function at any time t. Okay, so here what we must be interested in, around which axis is it, along y or x, then we use any of it. Okay, so velocity will be equal to the differential of the displacement function, which is a sine omega t divided by the changing time dt. So for us to get the velocity function, we need to look at how the displacement function changes with time. Okay, so here we are differentiating this with respect to time. Alright, okay, but a quick derivatives, because this is a trig function. Okay, now if you have a sine function and you want to differentiate this sine function with respect to the angle theta, then you have dy on d theta. This will be equal to a cosine function. So the differential of a sine function, so del dt of sine theta would always be equal to a cosine function. Okay, now if you happen to have y to be equal to sine 2 theta, here there is a coefficient to the angle. So this is a double angle because there is a coefficient 2. Okay, the differential of something, a function or a trig function of this nature will be dy on the theta will be equal to the differential of this. But take note, because this has a coefficient, it means what we have within the bracket is a function of a function, one function in another function. Okay, here the bigger function is sine 2 theta, and the daughter function would be 2 theta. So the differential of something like this will be equal to del the theta of the mother function sine 2 theta times del the theta of the daughter function 2 theta. So this is how we differentiate a function of a function. Okay, so the product or the result of this will be equal to, when you differentiate a sine function, it's equal to a cosine function. So cos 2 theta times, when you differentiate this, it is equal to the coefficient out, the theta on the theta. Okay, so in effect we have 2 cos 2 theta to be the differential of this this sine function. All right, so that is it. Now let's look at the differential of a cosine function, because at the end of it we are going to apply all this in our derivative. So let's go through the trig function sine and then cosine for just a simple function and then a function within another function. That's it, a function of a function. So we will look at a function y is equal to cos theta. Then we look at y is equal to a function of a function cos 2 theta. So y of cos theta, the differential of a cosine function, is equal to del the theta of cos theta, which is equal to the differential of a cosine function is equal to negative sine function. This is a rule which you have to actually learn. When you differentiate a cosine function, it's equal to the negative of a sine function. Okay, so let's have a function within another function, cos 2 theta. So the mother function here, the mother or the parent function is cos 2 theta. The daughter function is 2 theta. So you have to differentiate with respect to whatever variable of the mother function, and when you finish, you differentiate with respect to whatever variable the daughter function. So this will be equal to dy d theta will be equal to the differential of the mother function del d theta of cos 2 theta times del d theta of the daughter function 2 theta. So we have minus sine 2 theta, because when you differentiate a cosine function is equal to the sine function, times 2 out the theta on the theta. So now we have minus 2 sine 2 theta as a differential of y is equal to cos 2 theta. So these are the rules we are going to apply. Okay, all right. So we said that to to have an equation for the velocity function, we have to look at how the displacement function is changing with time. So del the theta of A sine omega t. Please don't forget this is actually y, the displacement function. We are looking at vibration oscillation along the y-axis, which is equal to del the theta of A sine omega t. Alright, so it means V would be equal to, this is the mother function. A is just a coefficient, and in differentiation the coefficient is not eliminated. Okay, so the presence of this coefficient, because it's a coefficient, multiplies throughout the subsequent derivatives. So because this is a coefficient, it will come out of it, and so we can have this as A times the differential of the mother function sine omega t, and this is coming, A is coming out because it's a coefficient, and the coefficient can be any whole number. It can be 2, 1, 2, blah blah, on and on. Alright, so when you are differentiating and there is a coefficient multiplying the function, it is repeated in subsequent differentials, so take note. So we have V being equal to A out. The mother function actually is of t of sine omega t, then the differential of the daughter function del the theta of omega t, similar to what we applied. Okay, now what is the differential of sine? When you differentiate sine function, it is equal to a cosine function. So cos omega t. Okay, let me bring it down because I could see the intensity of the light at that particular spot. So V will be equal to the differential of a sine function is equal to a cosine function times the differential of this is omega dt on dt. So we have V out. When you differentiate, okay, this is it. So A cos omega t by omega, giving us A omega cos omega t as the velocity function. So this is the velocity function or equation of a body in SHM. Okay, so at any time t. So when you are asked to calculate the velocity of the body, oscillating body, at any changing time, this is what you use in having your velocity of the oscillating body. Is that okay? This is what you use. Let's quickly consider some analysis. So we can quickly, let's consider this body. Okay. We earlier saw that when the body particle goes through one complete revolution, it takes the time period capital T for any complete revolution. So let's divide this time period into quadrants. So from here, when the time is 0 to this point, we have quarter of this, and then this point we have half of this period. Then this will give us 3/4 of the period, and when it comes back, we have the time for the one complete revolution. We want to determine the velocity of the body at these key points. Okay, at this point, and this point. Right. Okay. So when t is equal to 0, what's the velocity? Using the velocity function, v is equal to a omega cos omega t. Okay, let me clean this side for our analysis. Okay, so when t is equal to 0, when the particle is about to move, okay, what's the velocity of the particle? Yes, what's the displacement of the particle at this point? When we trace this point on the vertical axis, we realize that at this point the displacement is equal to 0. There's no displacement. And so if there is no displacement, then we expect 0 velocity because there's no change in displacement. Okay, so at the origin or at the equilibrium position, the displacement of the body is 0, and so its velocity would also be 0. But let's see how the equation, okay, or the velocity equation would give us. So v is equal to a omega cos of omega is 2 pi on t time, the time here is 0, and 0 times any value will be equal to 0. So we see that at the mean position, the velocity of the particle is 0 because there's no displacement. Alright, okay, so let's see the particle having moved from here to this point. When t is equal to quarter of the period, what is the velocity there? V is equal to a omega cos of 2 pi on t times the time is 1 on 4 t. So this is what we have. So we have a omega cos of pi on 2. Pi on 2 is in radian. Okay, so the pi on 2 is equal to 90. E cos of 90. We are changing the angular measurement in radians to degree. Okay, so but because cos 90 is also equal to 0, the velocity at this point will also be equal to 0. Okay, and these 2 points, okay, is the maximum displacement. So this is the amplitude and this is the other amplitude. These 2 points where we have the amplitude are called the extremes. So this is one extreme and then another extreme. So the velocity of the oscillating body at the extremes is equal to 0. Okay, and the reason is that yes, it is equal to 0 because let's look at this body. This is an oscillating body. If I displace it in one direction, okay, what is happening is that this is the initial point, this is the final point, and this point is the maximum point it can ever go, the extreme, one extreme. When it comes the other, another extreme. As the particle is oscillating, what happens is that as the object goes, the velocity decreases. So when it gets to the extreme, it has decreased to 0 because as it is going, its velocity will be decreasing. Okay, so at one extreme, it has decreased completely to 0. When it is coming back from 0, it is increasing, and because it has inertia and momentum, it crosses the main point and then comes to the other point. But as it's coming this way, the velocity will be decreasing, so it has decreased to 0 at one extreme. Then it goes back because it has inertial velocity. Then when it's going again, it decreases. Okay, from here it will be increasing. When crossing the main position, okay, it will be decreasing till it has decreased to the final edge. So at the extremes, the velocity is equal to 0 because it will decrease as it gets to one extreme and decrease as it gets to another extreme. So that's why the velocity of the oscillating body at the extremes is equal to 0. Alright. Now let's look at when it is here. Yes. The velocity of the particle over here, okay, the velocity of the particle over here at t is equal to half of the period, okay, v is equal to a omega cos of omega t. So a omega cos 2 pi on t times half t. Yes. Here we have cos of pi. So cos 180. Cos 180 is equal to -1. So we have minus a omega. Okay. Let's look at O again. When t is equal to 0, we have a omega cos omega times 0. So this part of it would give us a omega cos 0. Sorry, please let's take note of this. I think we made a mistake for generalizing this to be equal to 0. Since cos 0 is equal to 1, cos 0 is equal to 1. So please let's look at where I think we made a mistake over there. Yes, and so let's quickly correct it. It has just come to my realization. So the velocity when crossing at the mean point is equal to AW, the amplitude times the constant angular velocity. What it means is that the velocity of a body in simple harmonic motion is maximum, okay, when it's maximum. Let me go down this note because we are correcting a mistake. So the velocity is maximum when crossing the mean point. Please, the mean point is also the equilibrium position. So we have a maximum velocity from start, okay, from start, and then another maximum velocity over here, okay. So what we are saying is that at the mean point, when the displacement is equal to 0, when the displacement is equal to 0, we have the maximum velocity of the oscillating body occurring. At the amplitudes, okay, the velocity is equal to 0, but at a displacement at any point where y is equal to 0, we have the maximum velocity occurring, okay. So maximum velocity occurs here and also at this point. Alright, thank you for taking note of that earlier mistake. Alright, so this is another amplitude, one of the extremes, and so obviously once the velocity is equal to 0 here, the velocity will also be equal to 0. We can still prove though that at t is equal to 3/4 of the period, so at t is equal to 3/4 of the period, we have v is equal to a omega cos of 2 pi on t times 3/4 of t, okay, this and this 2, so we have cos of 3 pi on 2, and 3 pi on 2 is equal to 270. Cos of 270 is equal to 0. Therefore, cos of 270 is equal to 0. And so velocity there is equal to 0. Yes, as I said, this is another amplitude, so that's it. Now, when it comes back at t is equal to the time period, big T, velocity is equal to a omega cos of 2 pi on t times t. Okay, so we have a omega cos of 360. And what is cos 360? Cos 360 is equal to 1. Okay, cos 360 is equal to 1. So we have v giving us a omega. Alright, let's have a quick check. So cos 360 I want you to, check it yourself and then give me a quick feedback. Yes, that's right. Okay, so that's it. Please, this analysis can also be done using angles. You know, from this is 0 degrees, this is 90, this is 180, this is 270, and back is 360. And so we can also make this same analysis using angles instead of the time. Okay, so what I'm saying is that you change this division of the time period into angles instead. So we have, this is 0, then 360. When it comes back, this is 90, this is 180, this is 270. So what it means is that, don't forget, the angular displacement theta, which is omega t. So this is when you are expressing theta in terms of the time taken to make any. Okay, so when you don't want to use v is equal to a omega cos of omega t, then it has to be a omega cos of theta, because this theta, omega t is equal to theta. Then it means here you are expressing the velocity in terms of the angle it makes, not in terms of the time. So at theta is equal to 0 degrees, you have v is equal to a omega cos of 0, and cos 0 is equal to 1. So you have a omega. Okay, so maximum velocity occurs when the particle is crossing the mean position, where y, the displacement, is equal to 0. So at theta is equal to 90, you have v is equal to a omega cos of 90. Cos 90 is 0, and so v will be equal to 0 over here at one of the extremes. So you can do this same analysis using angles or in terms of the time technology. Alright, so here what are we doing? We are looking at velocity of the oscillating body, okay, at different times as the object moves from one point to another point. So we are calculating velocity using time. Now the other point is that, so this is a particle moving from this point to this point. What if you are not given the time, but you are given the displacement? So at a displacement of so and so, what is the velocity? Okay, this formula gives us the velocity in terms of time. Don't forget, omega is constant. The body moves at a constant angular velocity. A is the maximum displacement, the amplitude, which is also constant. The changing variable here is the time. What if you are not given time? That's the object, okay, changes, position changes with time, but the displacement, at a displacement of, let's say, y1, what is the velocity of the body? The particle moves from here at a displacement of y2. What is the velocity of the particle? So here, what are we given? We are given displacement, but we want you to find the velocity in terms of the changing displacement of the particle. Okay, and so our formula has to be changed from velocity in terms of time to velocity in terms of the displacement, and that's another point we are going to consider. All right, okay. So let's quickly have the velocity equation in terms of the displacement. Of the particle. So here you can be given the displacement along the y or the displacement along the x axis. So we have V is equal to E omega cos omega t. This is the displacement of the velocity of the oscillating body in terms of time. So velocity in terms of time. We want to change this to velocity in terms of the displacement of the particle. We know what is the displacement function. The displacement function y is equal to E sine omega t. So what it means is that before we can have the velocity function in terms of the displacement y or x, okay, don't forget the displacement along the x-axis too is E cos omega t. Okay, so we can have it either in terms of along the y-axis or along the x-axis. Okay, so before we can have the velocity in terms of the displacement y or x, we have to change this cosine function to a sine function, and when we're able to do that change, we can just substitute this into it. Okay, but what it also means is that as it stands, one thing we can do is that since V is equal to E omega cos omega t, we can realign this to be omega E cos omega t, and since this is equal to x, we can say that the velocity is equal to omega x. And this is when we are looking at the oscillation along the x-axis. Okay, oscillation the x-axis. Okay, along the x-axis. So this is the velocity of the particle in terms of displacement along the x-axis. Now along the y-axis, what can we do? We have V is equal to A omega cos omega t, and we want to express this sine function in terms of cosine function in terms of sine, so that we can substitute our y. Let's play around this equation. I'm sure we all agree with me that this can be rewritten as omega times E cos omega t. Okay, all right, so if this is it, then we can have this. We are just playing around the equation. We can have this as omega times the square root of A squared cos squared omega t, because when we take the square root of this, okay, let me rewrite it on top. So V is equal to A omega cos omega t. Okay, and this is the same as omega out times E cos omega t, so that we can rewrite this as, let me bring it down, since the density or the illumination at that point is so huge. omega times the square root of a squared cos squared omega t. Yes, when we do this, we haven't changed anything. When you take the square root of this, you come back to the same thing. So we haven't changed anything in the function here. Alright, we are just, as I said, we are just playing around. Alright, good. Now, from one of the Pythagorean triples, we know that sine squared of any function or angle omega t plus the cosine squared of it is equal to 1. If this is it, then when we make sine squared the subject, we have 1 minus cos squared omega t. Therefore, so let's make cos squared rather the subject. So this is cos squared rather. We are making this as a subject instead, so that this is equal to sine squared omega t. Okay. Cos omega t therefore is equal to the square root of 1 minus sine squared omega t. Okay, when we substitute this, or let's even substitute the square straight away. When we substitute cos squared omega t into this, we have v is equal to omega a squared out 1 minus sine squared omega t in omega out, we have a squared in minus a squared sine squared omega t. Okay, which is equal to omega times the square root of a squared minus a sine omega t all squared, and this term within the brackets is equal to y. Y is equal to a sine. So quickly we can substitute y in place of this to have this as omega times a squared minus y squared. I think it's not showing so well. Okay, I think it's better now. So this is it. We have v is equal to omega times that, where let's define the variables. Where v equals velocity, a equals amplitude, y equals displacement. So it means that the velocity of this omega in terms of the amplitude is equal to this. So this is the velocity of the oscillating body in terms of the amplitude, displacement. So whenever you are given the displacement, okay, at around the equilibrium position, this is how you can determine the velocity of the oscillating body. Okay, all right. Here, let's look at where the minimum and then the maximum velocity would occur. Just as we saw, it will occur at those same points. Okay, over here, and then over here. We saw that the velocity is maximum when crossing the mean point or the fixed point. Okay, and at the fixed point, y is equal to 0. If the displacement is equal to 0, when you put 0 here, you have v is equal to omega times the square root of a. So actually this is it, a squared minus 0. And so you have omega a, telling you that the velocity is maximum when the particle is crossing the mean point. It will also be maximum here, but the velocity is 0 here. At this point, what is the displacement? Okay, over at the extremes, the displacement is equal to the amplitude A. We have an amplitude here, we also have another amplitude here. So when y is equal to E, we have v is equal to omega times a squared minus a squared, because y is equal to a. And what is a squared minus a? This is 0. So it means that the velocity is minimum, okay, at the extremes, and maximum when crossing the mean point, or when crossing the from the equilibrium position. So take note, v maximum is equal to omega a. So this occurs when crossing the mean point or equilibrium position. Please, here you can't just say that the velocity is maximum at the mean point. If you say just at the mean point, when the particle is not moving and it's just there, it has no displacement either to have velocity. But when crossing, then you mean that the particle is in motion. If when crossing, then the velocity will be maximum when the particle is crossing the mean point. But you can't just say at the mean point. When the particle is at the mean point, it is not moving. But when crossing, it is moving. So the maximum velocity occurs when crossing the mean point or the equilibrium position. Then minimum, v minimum is equal to 0. Okay, this occurs at the extremes. Why? At the extremes, y is equal to the displacement is equal to the amplitude. Here, when crossing the y is equal to 0. And so if y is equal to 0, y is equal to a, then when you substitute it here, you have whatever we have under the bracket being equal to 0. And so you have the minimum velocity occurring there. The minimum velocity of a body in simple harmonic motion can can be equal to 0. So that's why we realize that when the particle is at the extremes, we have the minimum velocity carrying it. So these are the key concepts to be using: the velocity of the oscillating body in terms of the time, and then the velocity of the oscillating body in terms of its displacement. Okay, and that's it. Alright, thank you for staying tuned. Please continue to subscribe, share, and then pass your comments for a better feedback and all that, or for the improvement of the online tuition. Okay, please do it for me. I need your subscription, your sharing, and then your comments to do this thing better. Thank you for staying with me. Thank you for cooperating, and thank you for subscribing and sharing to my channel. Alright, we'll meet once again in another time to look at the acceleration of a body in simple harmonic motion. Yes, if we realize that as the object moves, its velocity is changing from the equilibrium position to the in between and then to the extremes. If the velocity is changing, then it also means that then the body is accelerating, because acceleration is change in velocity with time. So if we have a situation of changing velocity as the object moves, then the object is accelerating. So we'll look at the acceleration function of a body in simple harmonic motion, where it is minimum and where it is maximum, and then we later on look at some calculations therein. Alright, thank you very much, and bye bye.